about separations in metabolomics. My objectives for this talk are to give you an idea of why we even need to do a separation when we do mass spec-based metabolomics. I want you to understand some basic principles and goals of HPLC method development. And I want to give you an idea of common HPLC issues that you can spot when you're looking at your data. So where are we in the metabolomics workflow? And as several people have already pointed out, it is not necessarily a straight line. It is actually a circle or kind of an iterative process. Right now, we're analyzing our samples. So we've designed the experiment, we've done our sample prep, and now we want to make sure that we get the best possible outcome for further data processing and eventually for biological interpretation of our data. So everything that we do in this step is going to influence the further processing of our data. In metabolomics, we deal with very complex samples, and as Charles has indicated, with mass spectrometers, you usually have some kind of trade-off between fast analysis and a low limit of detection. So the faster you do your mass spec analysis, the higher your limit of detections are going to be. So the less sensitive your mass spec is going to be. And the purpose of chromatographic separations is basically to let our mass spec instruments operate as best as they can. And in order to do this, we want to reduce the complexity of the samples. We also want to separate isobaric compounds, because with mass spec, we can only distinguish things that have identical mass over charge. Chromatography can, depending on what kind of stationary and mobile phase we're using, can actually help distinguish the two, can separate them so that they can enter the mass spectrometer individually and be detected and quantified individually. And importantly, we use chromatographic separation techniques to reduce what's called the matrix effect in mass spectrometry. It is a function or a consequence of a large number of compounds entering the ion source simultaneously and then competing for the limited number of charges that are available. And that results in easily ionizable compounds being ionized over proportionally and being detected much more frequently than analytes that are less easy to ionize. And we want to avoid this by removing interfering compounds and spreading our sample out over the entire chromatogram. When we talk about mass spec compatible separation techniques, we can usually distinguish between adsorption-based techniques and electromigration-based techniques such as electrophoresis and ion mobility spectrometry, which we're not going to talk about today at all, but I just want to mention them because they exist and they are being used in metabolomics. And when we talk about chromatography, we usually mean either gas or liquid. And I will be focusing on liquid chromatography because it is, well, it's my specialty. Generally, in any type of chromatography, what we're using for a basis of the separation is a distribution of our analytes between a mobile phase and a stationary phase with different chemical properties. And the distribution of our analytes between those two are dependent on the analyte properties. So what happens when we're doing chromatography is we have our sample, and it is applied to the top of a chromatographic column. So basically, the stationary phase being held in some type of cartridge, while the mobile phase is continuously flowing through it. Now, our analytes are going to be distributed between the stationary phase and the mobile phase, depending on how high their affinity is for each of those phases. Now, an analyte that does not have much of an affinity to the stationary phase is going to migrate with the mobile phase through the column and is going to be detected very early in our analysis. That will be the orange particles in this image. Analytes that have kind of an intermediate affinity to both the mobile phase and the stationary phase are going to be retained for at least a certain time and are going to be detected later than anything that has no affinity to the stationary phase. And molecules that have a strong affinity to the stationary phase are going to be strongly retained and are going to appear late in the chromatogram. So based on the time it takes each individual analyte to be detected, we can already get some idea of the chemical properties, because we know that it must be a property that gives them a high affinity to the stationary phase. And Charles has already mentioned that, but there are several things that we can get out of a chromatogram. A chromatogram is a plot of signal intensity over time. And the time 0 is when we inject our sample onto the column. Now we can define a void time, or T0, which is the time it takes an unretained compound to travel through the entire column and be detected. And we can define retention times, which is the time it takes each compound that is even at least a little bit retained to travel through the column. And that retention time is a combination of the unspecific void time that it takes to travel the column and specific retention times that depend on the interaction of each analyte with the stationary phase. So again, the retention time gives us an idea of the qualities or the properties of our analytes. And the peak height or peak area give us quantitative information because they are proportional to the analyte concentration. And that is independent of the type of detector. That's true for a UV detector, and that's true for a mass spec detector. In metabolomics, like I mentioned, we use both GC and LC. And I'm going to be talking about, from here on out, exclusively about HPLC. And unless I say so, otherwise, I'm going to be talking about reverse phase chromatography, because this is by far the most widely used technique in metabolomics. As far as instrumentation is concerned, I've already mentioned that the stationary phase is usually contained in a column. In HPLC, it is often silica particles that can have a modified or unmodified surface. The purpose of silica is that it can be easily manufactured into very small particles with large surface area, and it is also very chemically stable. It's also stable against high pressures. Mobile phase is being moved through this column by a pump. That's one of the central components of each HPLC system. So we have a solvent reservoir up there. The pumps move the solvent through the system to the column that sits in here in a thermostatic compartment. We have an autosampler that can hold our samples until they are automatically injected. And then we have a detector. In this case, this is a UV detector. We usually talk about mass spec in this workshop. Now, what do we consider a good separation? What are the goals of our method development? And there are several, and I've listed them here. And I want to give a little bit of an explanation of what we're even looking for when we do HPLC method development. So first of all, ideally, we want to have symmetrical peaks. And the purpose of that is that symmetric peaks, Gauss-shaped peaks, are the easiest to integrate automatically. And automatic peak integration saves you a lot of time when you're doing data analysis, and it also really helps with the reproducibility. And in addition to that, symmetric peaks are also much easier to separate. That brings me to the next point. We want baseline separation of all our analytes, especially when we're dealing with mass spec. We want baseline separation of isobaric compounds, because those are the ones that we can't distinguish doing mass spec. Retention factors between 2 and 10, that is the retention time normalized by the void time that I showed earlier. Between 2 and 10 means that we want enough interaction between the stationary phase and the analyte to actually create chemical, or give the column the opportunity to chemically distinguish between the individual analytes. But at the same time, we do not want our separation to be extremely long, because that would be a waste of time and resources. And then finally, we want all our peaks of interest to be distributed over the entire chromatogram, and not all of them to come out at the front or to be retained until the very end of the analysis. And in order to achieve this good separation, we can work with modifying the analytes, we can change the stationary phase, and we can also modify the mobile phase system. I put here a generic workflow, and I don't want to go into detail on that, but I do want to stress that the basic part, the basis for each decision on what separation to choose should always be the properties of the target analytes. And then based on that, we can create ideal selectivity by choosing a suitable stationary phase and a mobile phase that fits the properties of the analytes in the stationary phase. And once we have that set up, we can modify the retention usually by changing mobile phase parameters such as temperature, composition, buffer content, and so on. And then we can also do some fine-tuning in terms of efficiency. For example, move towards smaller particles or core shell particles, as they're called, or move to longer columns, switch out one organic modifier for another, and do some optimization as far as pH control is concerned. Now, I said before that reverse phase is the most prevalent chromatographic mode that is used in chromatography, and so I want to spend at least a couple of minutes talking about how it works. So in reverse phase chromatography, the silica surface is modified with hydrophobic CH2, C18 usually, chains that provide a nonpolar surface, and this nonpolar surface can retain hydrophobic analytes. Now, in metabolomics, we deal with a lot of molecules that are very polar and very hydrophilic, and that makes them not exactly ideal targets for reverse phase chromatography. The reason why people still use it so much is that it's extremely stable, it's really well understood, and it is a retention mechanism that has only one major contributor, so it's relatively easy to control. But in order to better address polar metabolites, many people have started using HILIC or hydrophilic interaction chromatography, where we work with highly polar stationary phases that are better capable of retaining polar metabolites. And in this case, the retention is created by a water layer that forms on the surface of the polar stationary phase. And in addition to partitioning of polar metabolites from the organic mobile phase into that water-rich layer, because they have a high affinity for it, a lot of other molecular interactions can play a part in retention in HILIC. And that makes that type of chromatography much, much more difficult to control, because not only do you have to account for the water content in your mobile phase, but you also have to think about ionic interactions. You also have to think about potential hydrogen bonding between the surface of your stationary phase and your analytes, and so on. So that's not what I wanted to do. Going back to reverse phase, I mentioned briefly that you can modify selectivity and efficiency of a chromatographic separation by switching out one organic modifier for another. So as a reminder, in reverse phase, we have a nonpolar stationary phase, and therefore the stronger eluting solvent is also nonpolar. We usually start with a high aqueous mobile phase and then switch to, or slowly move to an organic mobile phase. But not all organic solvents have the same effect in reverse phase. As you can see here on the right, using methanol, or switching out methanol as the organic modifier for acetonitrile drastically reduces the retention time of some of the compounds. And interestingly, in HILIC, we have the exact opposite effect of acetonitrile and methanol. So adding methanol to a HILIC mobile phase actually decreases the retention time. I'm going to skip over this pretty much, just saying that we use buffers in HPLC usually to stabilize the ionization state of our analytes, because this state has an important influence on the separation. I want to give you a couple of things that you can use for developing HPLC methods that are just generally good practice, and they're usually related to how you care for your column. And I want to stress that you should really, really follow vendor recommendations. Do read the manual and do clean and store and regenerate the column exactly the way they suggest that you do. That gives it a much longer lifetime. It will also improve the reproducibility of your results, and it will save you a lot of money. Now let's talk a little bit about some common HPLC problems, how you can spot them in your data, and what you can do to fix them. Whenever I do quality control on my chromatographic data, the first thing that I look at are the pressure traces that almost every instrument records automatically. I want to make sure that for all my runs, the pressure curve stays the same. If I see spikes, that indicates that at some point my column or another part of my HPLC system got blocked. If I see a drop, that means that I probably have a leak somewhere that could cause me to lose part of my sample, and it will certainly lead to all my quantification results being off. Very often we see shifting retention times in our chromatograms, and that is usually a consequence of the column not being properly conditioned or non-specific adsorption, especially when we have biological samples. So each stationary phase has a certain amount of interactions that it can offer to analytes of interest, but it also, because it is made of silica and the silica has been modified in certain ways, it also has sites of adsorption that have nothing to do with the intended purpose. And in a complex sample such as plasma, for example, there's always going to be something that will attach to your column and not come off with the solvents that you're using. And over time, this stuff will either build up or it will create something irreproducible that interacts with your sample. And you don't want that to happen. So that's another argument for always regenerating your column properly. Peaks that have a weird shape, that are broad, that have shoulders, that have tailing, are always an indication that something is not going right with your chromatography and that you should probably address it. For example, a tailing peak, as the one that you can see down here, is relatively common for basic compounds in reverse phase chromatography, or just generally with all kinds of silica materials. And the reason for that is called the silanol effect. It means that silica has OH groups on the surface that have a certain pKa, so they're slightly acidic. Now, if you're operating at a pH around 4 or 5, part of these OH groups will be dissociated, and will be negatively charged. So what they're going to do is retain bases or positively charged compounds. And that causes this ugly unintended peak shape here. And there are several ways to get around that. So either use a lower pH that keeps the OH groups from being dissociated, or use end-capped stationary phases. Definitely every manufacturer provides them. Okay, so in summary, we want to do separations in metabolomics to make sure that we get the best out of our mass spec data. We should base our method choice on the properties of our target analytes. And I realize how that can be very difficult in untargeted metabolomics, where you're trying to get as much as you possibly can. As far as optimization is concerned, we can address stationary phase by careful choice. We can address the mobile phase by changing organic modifier, buffer content, buffer type. And we can also address the analyte itself by performing some kind of derivatization. The information that we can get out of the chromatogram in terms of our target analytes is qualitative. What kind of properties does it have? It can be quantitative or semi-quantitative based on the peak height, peak area. And we can also make sure that nothing went wrong with that part of our analysis by checking retention times and peak shapes. Here are some resources that I've used in putting this talk together and that I can really recommend if you want to learn more about how to develop HPLC methods. And if you have any questions, I gladly take them. Thank you. Questions?